Well, hi, we're the S Academy. Yes, we are going to be looking today at the ability to be able to take the data that we did yesterday with our rocket launchers, our Angry Bird launchers, and we want to be able to take that information, those three coordinates, and be able to do what we call write the function that models that path of the Angry Bird. So we're going to look at having that be a function, and we're going to write it in what's called the intercept form. That intercept form where we know where the x-intercepts are, and we use that bit of information along with the third point in the path of the Angry Bird flight, and be able to write a function that models it. And so we're going to look here. Let's look. This is the form of the equation that is intercept. We call it the intercept form. Well, yesterday you took you had a couple of intercepts where in your data of your table you had the launcher sitting at the 0, 0 coordinates. So that was one of the x-intercepts. That's where your Angry Bird was when it was in the launcher. And so that one of those, instead of H and K, I think the textbooks that you're using use the letters Q and P to be those intercepts in which we are subtracting from the x-coordinate, which is modeling the horizontal position of that path of flight. And so if we take that x and subtract away one of those x coordinates, again the x value where that Angry Bird was sitting when it was on the ground, where the launcher is on the ground. And again, depicting that graphically, we have the launcher sitting at the 0, 0. What's the x-coordinate? 0. So then we launch, and it takes some path and comes down and hits the ground again. I'm just making up numbers, but the x-coordinate there would be, say, some number, 100. Y-coordinate being 0. That's the x-intercept. This is an x-intercept, so you had those two values. So we're going to take one of those values, being 0, the x-coordinate value is 0, and subtract that, and then we're going to take that other value, that other x-coordinate of the x-intercepts, and we will subtract that away from the value of x as we have it. Again, A is what we know to be that A value of that quadratic term. So we have that sitting out in front and multiplying. Well, we have lots of letters. Again, in function notation, we know that we could write y for that function notation. We've learned that those are interchangeable. They mean the same thing, just being able to do different aspects of it. So instead of writing the function notation, we can write that y value. This allows us now to see I've got a y letter, an a variable, and an x variable still left in my equation. I need to solve for a, and so I need numbers that we could plug in for both y and for x that go through different than the 2 points that we already have. So again, you took data yesterday where you found a coordinate that your path went through when it hit the table. That was your third point on your table of data that you have, and you collected for each of the angles and the forces that you were using in launching your rockets or your Angry Bird. Well, I'm just going to make a number up again here, saying that it was, in this case it looks like that's about 70, and I'm going to make up a number of about 30, just to make up those are the coordinates. So that's a point that we measured that the Angry Bird was going through. I can type in, now for the y, I can type everywhere I see y, I can write 30. And everywhere I see x, I can write 70. Because that is the value that it was going through. So that's the other coordinate. X is 70 and y is 30. So I just wrote that in for those values. Now I have an equation sitting here that only one letter left. And now I can easily, or algebraically, then isolate what a is. We first take the numbers and simplify those. Can I multiply these two? negative 200 sorry, 2100, missed the decimal there, 2 zeros and 21, it's negative in value. And then to isolate the a, it's being multiplied, I divide. Just using our simple algebra manipulation to get that variable by itself, I get this number, simplifying that fraction, to be what a is. So now I can go back up into the function notation and write the values for everything that I have letter-wise, value-wise, except for the x or the f of x and the x coordinate itself, and y. So I can rewrite. I want a function notation where the function as it relates to x, leaving x as it is, but substituting back in values for the p and the q, the x-intercepts, and then the a value now that we have algebraically written. So the function modeling our path for this particular angry bird, a now we know to be negative 1/70th, and I'm going to multiply that to x because x minus 0 is x, and then x minus 100. That is the intercept form of the path of that angry bird. So now we can use this function. In a future lesson, we're going to show you how now to enter that into the graphing calculators, just like you did your algebraic artwork, and enter that into your graphing calculator so that you can find any path, any coordinate through that path of the angry bird. And if we at competition time sit a pig in the path and give you that coordinate, you can then know, through sitting here, I can pull up the data, the table, and find that this path, this function, modeling this force and distance, can get force and angle, goes right through that coordinate. I know to choose it to shoot that pig at competition time during the angry bird competition. So that's a way of calibrating. We know that that angle and that force that you gathered the data on that went through these 3 points, we now know the function that models that path. So anywhere along that path, if a pig is placed at the vertex, here, there, anywhere along that path, you know to shoot that angle with that force because it takes you through that algebraic pathwork to hit a pig anywhere in there. That's how you can use mathematics. That's the power of algebra functions and graphs that make us angry bird competitors. You being the academic athletes that you are, we are the Ask Academy.